Hello people, this is video tutorial number 10 in the motion design uh, playlist for 3D Experience. It's a it's a it's a essentially a kinematic problem, but I'll refer to it as a dynamic one, and it's the kind of thing that probably you did in high school physics. But that's okay. I want to show you how you can use a marker. It's a continuation of video 9 for imposing initial conditions. The situation is like this. We have a mountain, a volcano, and there is a hot rock on the top, which is being ejected at velocity of 25 meter per second. What we at an angle that you see there, what we want to know is when will it hit the ground? This is 20 meters high, and what is the velocity when it hits the ground? Now, the reason I do things like this, these elementary problem, is essentially to reinforce some of the concept in the context of problems that we have analytical solution for it, including this high school physics problem. It's actually coming from that source, that internet site where they actually have solved it. The mass of the rock doesn't matter because we're doing the kinematics. We're not asking about forces and things like that. So it turns out that assuming that the gravity is 9.8 meter per second squared, it takes almost 4 seconds to hit the ground. And the components of velocity in the y and z direction are given as these numbers. Now, the only change that I made with the example in the site is they refer to these axes as x and y. I changed it to y and z because it's easier to draw it like that on in 3D experience. Now, I want to remind you that the initial conditions are imposed through this icon, and we're going to do it with a marker instead of a joint. I don't have any joints, as you'll see. And once you apply the initial conditions, you have to do the initial state solve to see whether the rock is positioned in the correct spot or not. It's a simple problem. Please watch video 9 if this doesn't make sense. Okay, so let's go ahead here. We start with an assembly design. There's only a single part here, and that single part is uh, an object which I make it cylindrical. It makes no difference. That's really the rock. Okay, so I'm going to insert the 3D part, and I'm going to call it the rock, which is being ejected out of the volcano. Dimensions of it and things like that don't really matter. When you go make it. So, for example, on that horizontal plane, I will sketch a circle. Just so that it's consistent dimension-wise with the height of the mountain. I'll make this thing maybe 0.1, 10 centimeter. Okay, exit, and pad it by also 10 centimeters. Now, in tutorial 9, I created a point at the centroid of this and made sure that that point is being lifted up to the location that around 20 meters high. But in this particular problem, because these dimension, I made it small, almost 10 centimeter, it really doesn't matter. I can use the marker that's automatically created by by the software. Okay, please, if these things don't make sense, watch video 9. Okay, where I've said some very basic elementary things about markers. All right, so that's pretty much it. I don't even have to create the ground, another part which is the ground, because or earth or land, bottom of the mountain, because automatically when you do motion design, a ground is created for you. Okay, I don't have to do. If it helps, I can make it, but it's not necessary. All right, let's go all the way to the top. And if it's helpful, what I'm going to do is I'm going to transfer this thing. You'll see why I'm going to do that. I'm going to use the compass to translate this thing. You'll see why in a minute. Okay. Okay. Now we're going to go to motion design. Okay. Motion design. And notice that a, a ground has been created, which is right there. Remember, if I had not translated this thing, these would have been on top of each other, and there's nothing wrong with it. It's just that I want to show you that a ground has been created, and when I say move it to that location, location 20-meter high, is with respect to this fellow. Okay. Now, the default properties of steel have been associated with this block, but it really doesn't matter. This is kinematics. It makes no difference. It's not steel, but it's okay. Now, gravity has been defined down here, and if you want to change that, instead of 9.81 to 9.8, it really doesn't matter. I can make it 9.8. Now, what I want to do is I don't want this thing to be on the ground. I want it 20 meters high. So we're going to go to mechanism. We're going to go to initial conditions with a marker. Which marker? That marker. I want this thing to be moved to the right location. And what do we want? We want translation and not rotation. Translation. We want translation. For translation in x direction, I want specify position and velocity. X direction things don't move. Okay, so yeah, sure. If I wanted to move in the x direction, this being the x, let me see what I had here. Actually, y. I said y, right? Okay. So I don't want anything to move in the x direction. So velocity is 0, position is 0. Fine. And now in the y direction, I want the position to be 0, position and velocity, position to be 0, and y to be, if you take a look at this, you take the 25 multiplied by cosine of 35 degrees, you're going to get component of velocity in the y direction. And if you do that in the y direction, 25 times cosine of, let me see, times cosine of 35 degrees is going to be 20.479. So 20.479. And for Z, again, position and velocity, I'm on the height of 20 meters high, and 25 times sine of 35 degrees, and that's going to be 14.334. 14.334. And then we say, okay. So notice that this marker is going to get transferred to x of 0, y of 0, and height of 20 meters, z of 20 meters. And the velocities are going to be these things and nothing in the x direction. So we say, okay. Now remember, you did it, but it's not going to show here. So what you have to do is you go here and say initial solid state, initial solid state. So it's going to move that thing 20 meters high right up there. Where is it? Oh my God. It's up there, right up there. You can see that. All right. Now, by the way, if I had put this marker at the centroid, as I did it in uh, this this flipping, this rotation may not have happened. It doesn't matter for my problem. and it could be an artifact. I'm not 100% sure, but anyway, just leave it the way it is. That's pretty much it. So we go to simulation. Oh, how many seconds we want? This is going to be over default 5 second interval. So that's fine. That's okay because we know that after 4 seconds it's going to hit the ground. So we'll see. First of all, let me put this thing in with the view in the front direction. And so this, as I do the animation, it's going to go on a parabola and it's going to go past the horizontal axis because 5 seconds. So let's see now. We go to results. Let me select this results and animate, and you can see that. So let's go ahead. Ooh, where you go? Oh, right there. Go back. You can see that, okay? As a matter of fact, let me go to 4 seconds instead of 5. Run it. Simulate it. There. Now, let's plot a few things. 2D plot. Let me plot the stuff about what is that? Stuff about the rock. What do I want? I want the position, not X. Position of X is always 0. Do Y and well, let's do Y. Notice that. Okay. Notice what happens is that. Oh, actually, I don't want Y. I want Z, the height to be 0, right? Hitting the ground. There. So notice that initially height of 20, and then it's going to go down here at around 3.9 something. It's going to be right there, around 4 seconds. It's going to hit the z equal to 0. We can see that. And if you want the velocities, so let me get rid of this plot. If you want the velocities in the y and z direction, because x direction is going to be 0, it doesn't move in there. Notice that initially, for example, this one is z velocity 14 point something, and then it's going to go to roughly 24, right? 24, and then the other one is always a constant. The y velocity is always a constant, 20. So yes, we solved a high school physics problem with 3D experience motion design. Good luck. Other ways of